Okay. Quantum physics, it is completely a new chapter with respect to the A-level syllabus. And I will be going over the big ideas, first of all, what it is, what the theory really talks about, and it is probably one of the more fun things you'll be studying in physics in general. Where, um, so what is quantum physics? Now, for this, you need to understand the essence of two basic ideas. One, where we start questioning how particles really behave. Okay? And the two ideas that we explore is, well, is it that everything in the universe, especially when talking about stuff like light, is it simply a particle, or is it simply that it is a wave? Okay? And all of these ideas that we explore, is it wave? Is it a particle? That is to say, let's say I have a water bottle. Is it simply a particle, or does it also have wave-like feature? And then when we have a conversation about light, right? Then we also explore two ideas. Is it simply a wave, or is it simply a particle? And as you study higher level stuffs in university or whatever, you will see that, well, these are relevant things to explore and relevant ideas to understand, because it gives us a viewpoint as to how things exist, why things exist, and how we can predict certain things. Okay. So I will give you a bit of an understanding of why this idea of wave and particle really exists through experiments, which is in your syllabus. Okay. So the main idea we explore is via the lens of light. Okay. So light, we say, you typically, the EM waves, broad word, I would say, is EM wave, electromagnetic waves. Fair? This, to act like classical waves. It has a frequency, yes, and a wavelength, and it transfers some amount of energy. So it has wave-like feature. Okay. Now, the other phenomena that we have discovered, and it will be proven in this syllabus as well, is it also acts like a singular particle. Like, for example, a particle and particle collision, right? So apparently lights act like this. They can collide with other particles. They can transfer energy, like change in momentum can take place. So these are ideas that we only attach to particles in our real life. For example, balls, or basketballs, and to be specific, or bowling balls, spins and bowling balls. There's a transfer of energy. There's a momentum change. That's why things are happening. So they behave like particles. It turns out to be light also behaves like that. That is it. Uh, behaves like a particle as well. And towards the beginning, when I was saying that these two ideas I can explore with respect to light, but also everything. It turns out to be when you do advanced stuffs that, well, and it is also in your syllabus over here, the Broglie wavelength. So you explore that even with simple objects, they also have wave-like features. Even though they're particles, they are, some sort of an object, but they also carry wave-like features. It just so happens to be. So we'll explore these ideas, but we will be first of all looking from the lens of light. What is quantum physics? And is it true that waves behave like a particle? Let's explore. Till now, we know that. Till now, we know that EM waves, for example, are typically behave like waves. And why do we say that? That EM waves have certain features or go through certain phenomena that easily describe that they're wave-like. That is, one is diffraction. So when you have waves, for example, a typical example would be is you have a wavefront of water, right? You have a bunch of water waves. These consider these to be crests. So like the top position of the water wave, right? And they pass through, let's say, two slits. Okay, these two slits. What you will see is the waveform bends. So the crests have now bent. So they have diffracted. And these features, this action itself is a definition or an indicator of a wave-like feature. Okay, so of what? Water waves are classical waves. They are what? Classical waves. Another example of classical waves would be, let's say, rope. Okay, if you have a rope attached here and you have this amount of rope and you start, you have your hand over here, okay, and you start swinging this as in you move it up and down and it creates a wave, and this is a typical classical wave. So waves are waves, no difference there. So, and typical classical waves will go through something called diffraction, which I just showed with the example of water. And there is also the interference. What is interference? That two waves interact with each other and they can sum up or subtract. That is, they can, um, there is what is it? Superposition of the waves. They superpose between on each other. Okay, they superimpose on each other. That is to say that if you have a wave like this, and then you have a wave like this, and then you have a wave like this, ultimately all of these points, let's say at this point there is this much, at this point there is this wave and also this wave. So ultimately, you know what will happen? This will create this will create one ultimate wave. Okay, it will create one ultimate wave because they're superposing, and ultimately what we get is a cancellation of a bunch of amplitude and an addition of a bunch of amplitude, and we get one lasting wave. So this superposition between the waves is a definition of classical wave. But why do I say this? Because you will see this in again the diffraction example. You want to know how? So no, what have I drawn? Why this? So in this same two slit example, you will see when the diffracted waves come out. Okay, when they do come out, when you see these junctions between these diffracted wave fronts, you will see when these two wave fronts meet, they create a peak, and when there is some sort of a trough, right? Some sort of a low that is of a wave, right? And they add up, then it is the depth in the water is larger. Okay, the depth in the water is larger in those areas. So if you just check, you have two sources of wave in a in a pond filled with water, and you somehow create wave in the pond. Let's say you're using a spoon to hit on the this is the edge of the ground and there's water over here. Simple experiment. You take a spoon or a metal rod and hit this part multiple times and hit this part multiple times. A bunch of wave will be created, a bunch of wave fronts will be created, and you can see the superposition between the wave fronts itself, how the you know um, how they sum up and how they also cancel each other. So it's a very interesting thing to watch, right? Um, this is called interference. They interfere with each other. Classical waves tend to do this. So that's one thing. Next, what we realize is since these things are happening with light waves, right? With EM radiation in general, electromagnetic radiation, there's radio waves, there's all sorts of waves. Since these happen, we easily attribute the classical wave notion to our electromagnetic radiation. But this is not where the conversation ends. Scientists have also seen that EM waves um, exhibit particle like features. And the way we can figure it out, there are a lot. There is mm, Compton scattering. The Compton scattering is not in the syllabus. There's Compton scattering. There is, we can talk about line spectra, of course. Uh, you can talk about line spectra, you can talk about photoelectric emission. See, the photoelectric emission, I say, is the bane of this. It's the not the easiest to understand, or It is just something that so elaborately and so nicely exhibits the idea of having particle-like feature for a wave, and we'll explore that the first thing. So, what does it mean for a particle to exist? I'm telling you that scientists have figured out that waves apparently behave like particles. But what does it really mean? What it really means is, let's say you have a photon. Okay, what is a photon? We say it's a packet of energy. What do we say? It is a packet of energy, and we attribute these photons to exhibiting something called light. So, whenever we say or talk about there being light, right? Whenever we say there's light, we say it's emitting photons. Okay, we say they're emitting photons. So it's the multiple packets of energy being released. So we say that these photons are the particles that essentially make up the EM radiation. It is creating the classical wave, apparently. So let's explore this more. Um, these photons, we consider these to be massless, or we consider them to be packets of energy, and energy we don't really consider them to have any sort of mass. So we consider these massless quantums or particles. Okay, these are considered massless quantums or particles. Note these. Fair. Now the next conversation is, how can we prove this, right? Often a common misunderstanding for us is, give me a moment, please, give me a moment. Yes. So as I was saying, we have to explore the idea of how to prove that they're like packets of energy. And I will also pose another thing, that why is it so counterintuitive for us to think that light essentially is a particle? Why is it so difficult to comprehend? One of the ways that I can explain this is, we often tend to think that we have, let's say, a light source, right? You have a light source and you have a metal plate over here, right? You have a metal plate over here. And light, we consider to be a classical wave. It goes and transfers energy to the metal plate and is a constant supply of energy. So typically with classical waves, it makes sense. Classical waves transfer energy. And the longer you have this light source on a metal plate, as long as you keep it with the same intensity, the metal plate will grow like warmer. The temperature of the metal plate increases. So it sort of shows the classical nature in my eyes, and it becomes counterintuitive for me or hard for me to comprehend that there are particles in light waves. Because for me, I see classical waves as a way that there's a continuous source or flow of energy hitting the metal plate, which is why it keeps increasing in temperature. But there are nuances to this. If indeed light is particle, how is this happening? You can ponder about it. It's simple. Uh, it's simply a transfer of energy, and it is continuous in nature, but it is simply that each photon is transferring a certain amount of energy, and it is not that it is, in some way it is a continuous transfer of energy, but it's just that one photon goes, transfers energy, second photon goes, transfers energy, third goes, transfers energy. I mean, there's more technicality to it, and you'll see what happens. But you know, this is how we can express the particle nature of the light. And typically, when you would just think of a wave, this is how you just think of a wave. It's simply a wave. It is a constant stream of energy. Let's just say that. That's the idea in our head. There is a constant stream of energy. We just don't distinguish this wave as individual particles, do we? Okay. So it's very hard to comprehend in some nature. Okay. And the other thing is, nobody really understands quantum physics. So it's if it's hard to comprehend, that is because there's nothing to comprehend really. It's we are not yet there, but I'll tell you what, it's very difficult to completely understand what's really happening at the smallest scale. Anyways, so right now we have established one thing, that apparently a light can express particle-like features and classical wave-like features. Good. So if these light sources, these classical waves, are indeed particles, then as mentioned, that each of these particles, which we call photons, have a certain amount of energy. That is what we say. Now, what is this energy? How much energy is it that these each photon? I'm not necessarily saying this is how photons look, uh, but I'm just trying to paint a picture. Let's say these are the individual photons in a light source. Okay, so how do we figure out how much energy each of these photons have? That is, how much energy will each of these photons transfer to the, let's say, metal plate? Now that can be found out by this neat equation. Okay, how do you find it? We take the help of something called Planck's constant. So energy of a photon can be expressed as Planck's constant times frequency of the wave. But wait a minute, where did this wave come from? Confusing, right? So what it means by frequency of the wave is, ultimately, one way to put it is, think of the photons as traveling as a wave, as a constant. It is a stream of photon going through space and time and traveling with a frequency, with a wave. So when I say energy of a photon, what essentially I'm saying in this expression is, you multiply Planck's constant, which is a constant, times the frequency at which the photons are traveling. That is the frequency of the wave. That is how you can express this equation. Okay. So the higher the energy is of a photon, it vibrates at a higher frequency, or it travels as a wave with a higher frequency. Okay, there are way more nuances to it. I am establishing that. So, I mean, you will learn as you proceed, but this is one way to put it, and a very simple way to put it, which is not entirely wrong. Okay, and so till now, what did we establish? Waves apparently act like particles, which were called photons. I mean, not waves, light waves specifically. So they have particle-like feature, and those particles are necessarily called photons. And these photons, I can find out the energy, which is E is equals to hf. Planck's constant, probably 6.34 into 10 to the power minus 34, something along those lines. No, I'm wrong. 6.63 into 10 to the power minus 37. This is the Planck's constant. Okay, fair. So you basically multiply the Planck's constant, whatever the constant is, times the frequency of the particle, and frequency of the photon, and you get the energy of the photon. Again, higher energy photon will vibrate at a higher frequency. Very good. Now there is this notion of you guys know this. Okay, do you guys know this, that um, there are different wavelengths for different colors of light, and why are they different colors? Oh, nice. My colors exactly matched the letters. Interesting. Anyways, so the color of the light is different for what reason? Why do you think red is red, orange is orange, yellow is yellow, and green is green? Why do you think that? Can you tell me? What is making them different in color? Any idea? No?
Is it the
Okay,
wavelengths?
exactly. So it is the wavelength of the color. So the red has a different wavelength in comparison to the violet. So red is red simply because it has a different wavelength. And orange is orange simply because it has a different wavelength, nothing else. So red has we say, longer wavelength. So do you guys know this? Formula V is equals to F lambda So if wavelength is longer, frequency is lower. Okay, and makes sense. So if frequency is longer, what happens? Sorry, frequency is shorter, what happens? That means energy is less because they're proportional. So this red has longer wavelength, hence less frequency, hence less energy. Which one amongst Rogbiv has the highest energy, do you think? By the logic I followed.
Violet.
Perfect. So violet has the highest amount of energy. And why is that? It has the shortest wavelength, right? It has the shortest wavelength, hence frequency is the highest. And if frequency is the highest, that simply means energy is higher. This logic need to be flag posted in the brain. Very important. Okay? This simple logic will help you a lot of times. This is the Planck's constant. And we can also rearrange or re-express this in a different way. How do we re-express? What do we change? So energy of a photon, I can introduce a different formula for frequency, which is going to be velocity by lambda. Okay? And velocity, except for v, I can write it as c. Why can I write it as c? Speed of light. Because we are working with light only. Okay? Speed of light. So h times speed of light divided by lambda is equals to the energy of the particle. What did we include? Make sense? Very good. So this is the energy of a particle. Till now, I told you guys that energy of a particle is expressed by this equation, and that light travels as both a classical wave and as a bunch of particles. Good, but I didn't give you the proof, and I'm going to be giving the proof very soon. Okay, so by the way, how did we get this equation? It's pretty much an experiment, and we found this proportionality that energy of a particle tends to increase as the frequency of the particles increase, and if that is true, then it is simply a line through origin, and it has a gradient, and that gradient turns out to be Planck's constant. This is an experiment that may have explored in paper 5 or thought about or worked through paper 4 questions as well. It's a very common thing. Now, another thing I will explain right before I get into photoelectric effect, which is the proof that light travels as a particle or light consists of particle. And it is important to establish because this is the notion of energy itself. Okay? Notion of how to express energy in this chapter and many more in physics that is in your syllabus. So energy can often be expressed in terms of EV or 1 electron volt. Okay, and I will explain that. So 1 electron volt is the energy gained by an electron when accelerated from rest to a position to a potential difference of 1 volt. So let's say there is a grounded plate that is grounded is not in its habit, but I mean it is just plugged into the ground. That means it has zero potential. Okay, so and then there is 1 volt plate. Okay, and there's an electric field over here. Okay, so if you release electrons over here, what will happen? It rushes to the other plate. That is pretty much what happens. So there's an electric field line over here in this direction, right? So, sorry, electric field line is in this direction. That is the electric field line. The white ones I just drew is the electric field line, and electron travels opposite to the field line. Good. Mhm. Yeah. So now my point is that what is electron volt? What is 1 electron volt? It is simply the energy the electron that the electron gains when it is accelerated from rest to a difference of 1 volt in potential. Very simple. So basically, how much energy is this? How much energy do you think this would be? So it is 1 electron volt. Okay. So if you want to convert this to energy, let's actually try an example. That would be better. I'll give you an amount that is, let's say it's 3.7 into 10 to the power minus 19 joules. So I'm giving you the energy. And I want to convert to EV, which is probably more often. This is probably something that you have to do more often. So because they'll say write your answer in EV. So this is probably the more important conversion, but it's the same. You just do the opposite when you're doing electron volt to joules. So, anyways, the energy in 1 volt, what is it? It is very simple. What is the voltage I'm talking about? One. What is the charge on one electron? 1.6 into 10 to the power minus 19. Okay. And why does this make sense? Energy in 1 volt is 1.6 into 10 to the power minus 19 times 1. Why does this make sense? Do you guys remember what voltage formula is? Work done per unit charge. And work done is equal to voltage times charge. Very simple. What is the voltage it goes through and how much charge went through that voltage? When we're saying 1 EV, what is it? How much charge? 1.6 into 10 to the power minus 19 charge, because one electron has this much charge. And how much voltage it went through? 1 volt. Okay, 1 volt and the charge of the particle. Very simple. This is 1 EV. This is what? 1 EV. So how many joules of energy? 1.6 into 10 to the power minus 19 joules. Okay. So the number of EV needed for this amount of joules is what? 3.7 by 1.6 essentially. 10 into minus 19, sorry, 10 to the power minus 19 gets cancelled. It's essentially 2.31 EV. This conversion, important. You need to understand this conversion. Okay, so essentially, this is the energy gained by one electron being accelerated between 2.31 volts. Okay, you can also say this a different way. You shouldn't, but that's not technically wrong. That if you have 2.31 electrons going through 1 volt, this is the energy gained by 2.31 electrons. But why do I say it is wrong to say? You can't fundamentally break down electrons. You cannot. 2.31 doesn't make sense. So what do we say? It is quantized. Probably. So I forgot the word, but yeah, probably it's quantized. So the word I'm looking for is it is unbreakable. E, one electron, is a fundamental unit in some sense. You can't have decimal of it or a portion of it. It is you can't have less than one electron and call it an electron. Okay? So it is quantized in essence. So you can have one, two integer numbers. So either this doesn't make sense to say. You can't say 2.31 electrons going through 1 volt. Doesn't make sense. So that's why we say it is the energy required by one electron being accelerated between 2.31 volts. If your answer is 2.31 electron volt. Okay, good. Makes sense. Any confusion to this point? Let me know. Conversion we just did. Good. And I will be passing to photoelectric effect, where I'll be proving to you that electrons do act like particles, not electrons. My bad, photons. That is light. Light acts like particles, i.e., photons. Okay, this is the proof. So, what is photoelectric effect? It is a phenomena in which electrons are emitted from the surface of a metal upon the absorption of electromagnetic radiation. What is the photoelectric effect? EM waves come in. We have light or some sort of wave coming in that is carrying energy. It hit the electrons, transfer energy to the electrons. Electrons are like, damn, I have a lot of energy. I will escape. Okay. It no longer needs to be bound. By the way, between a positive and a negative charge, EPE is, oops, Negative or positive? Is there potential energy negative or positive between a positive and negative charge, opposite charge? So between a positive and negative charge, do you think the PE is positive or negative? So it's attractive forces. Okay. So essentially, in case of whenever you have attractive charges, we are going to say the EPE is negative because they are negative electric potential. Because essentially they are attracted. So you need energy to pull them apart. Okay. So I need energy basically pull them apart. Okay. So when I transfer energy, EM waves comes in, hits the electrons, transfers energy to the electrons. I'm giving it energy for it to be able to cut out of this attraction between the positive and the negative charge. So when I transfer this enough energy, it is set free, you can say. It is no longer bound by the orbit because I have transferred my energy. The EM wave transfers its energy to the electron. This is essentially what's happening. Okay, perfect. Now, observations, how do we prove this? So as the radiation hits the metal, the photoelectrons are emitted instantly. It's a very instantaneous process. The moment the photoelectrons are, sorry, the moment the photoelectrons are hit by the radiation, they're emitted. And by the way, why are these called photoelectrons? Photoelectrons. Why are they called this? Because they were hit by a photon and then emitted. They're still electrons. It's the same. This and this is same. It's simply that they were hit by a photon and emitted. So after being hit by a photon and being emitted, they're called photoelectrons. That is it. They're electrons, or they're just electrons. There's no difference in a sense. Okay. Next, photoelectrons will only be emitted if the radiation of the photons, that is energy of the photons, meet the threshold frequency or is above that. If below, the electron from the metal cannot jump from their orbitals and escape. What does this entire point mean? I'll explain. So essentially, the electrons are bound by a certain attractive force, by a certain electric potential energy between the positive charge and the negative charge, that is, they're in orbit. All of these electrons are in orbit. Okay. They can also be like free electrons through the conductor, no problem. But still, they are bounded in the material by attractive forces between the positive charges and the negative charges. Now, they have a certain threshold frequency. And what do we know about frequency? It can be said in terms of energy as well. So energy can be expressed in terms of frequency. So when I say there's a threshold frequency, I essentially say there's a threshold energy. That is, it needs a certain amount of energy. The electrons need a certain amount of energy to be set free. Okay. Hence, automatically, there's something called a threshold frequency. If I need 30 joules of, let's say, energy, essentially, I will probably say that I need around 6 point, let's say, 3, 5 into 10 to the power, I don't know, 37, 38, 39, 40. It's I need this hertz of frequency, 5 into 10 to the power 40 hertz for the electron to be set free. Why? Because the electrons are bounded in between themselves, that is positive and negative charge, with an electric potential energy of, let's say, minus 30 joules. Okay. And this is the energy needed for the electrons to be set free. Whichever orbit they're in, different orbits will have different energy. Nonetheless, let's say it's a last orbit. last valence shell, and the electrons need this amount of energy to be set free. And inherently, because of that energy requirement, the frequency required is 5 into 10 to the power 40 hertz. And if this is the amount of energy required, then the waves coming in should have what? 5 into 10 to the power 40 hertz or more, or more. So this is the threshold frequency. So the wave coming in should have that frequency. Clear? Very good. So when that amount of energy comes in, electrons are free and they escape. If it's more than that, the electrons will still escape, but with a certain velocity. With a certain velocity. That is, they will have a kinetic energy, excess kinetic energy. They were set free. So basically, when they're bound together, they have a negative electric potential energy. When I provide this amount of energy, when I provide this amount of frequency, that is exactly 30 joules of energy by the wavelength, that is EM wave. So the total energy becomes minus 30 plus 30 joules, 0. But let's say I provide 6 into 10 to the power 40. What happens then? I've provided, let's say, more energy. Essentially, it would be along the lines of, I'm not sure. Let's say three joules of extra energy. Okay, let's say there is 3 joules of extra energy. What happens in this case? This 3 joule of extra energy that I provided, sure, the electrons will be free, but they will be free with extra kinetic energy. Okay, so that 3 joule becomes kinetic energy. Good, good, good. So basically, we know that there's a certain threshold frequency that the EM waves need to have for the electrons to escape. Now, for classical waves, we know that intensity is related to energy, and to increase the intensity, we increase amplitude. However, in quantum theory, we increase the energy by increasing the frequency of radiation. That is going from, let's say, a lower frequency light wave to high frequency light wave, hence increasing the energy of each photon. So essentially, when we're talking about classical waves, we are more concerned about, when we're transferring energy, I'm more concerned about the amplitude of the wave. If it has a higher amplitude or a higher intensity, intensity is proportional, square proportion to amplitude. So basically, if you have a higher intensity, higher amplitude, higher energy transfer. But when I'm talking about this case, in quantum theory, you know what I say? I'm less concerned about that. That is not what I'm worried about. What I'm worried about is the frequency of the wave. So if this is a high frequency wave, it has higher energy. Okay? High frequency wave will have a higher energy. That is, each photon will have a higher energy. Clear? Each photon has a higher energy. If each photon has a higher energy, then each electron that is emitted after individual collision, so one photon, this is one photon, this is one photon, comes and collides with one electron only, transfers all the energy, and the electron leaves with, let's say, extra energy. That is, I provided more than enough, more than the threshold frequency. Great. So if I want to transfer more energy to the electron, what do? I use a high frequency light. As opposed to, in classical wave theory, what we say is increase the amplitude of the wave. Okay, in this case, what am I doing? I'm increasing the frequency. That is by choosing photons that are traveling with a higher frequency or has more energy. Great. So when the frequency of, let's say, what I'm trying to say over here is, when the frequency of the electromagnetic radiation increases, they hit the electron with more energy, as we know of E is equals to hf. So now, due to that, the electrons get to escape with a certain amount of kinetic energy, and we call this energy maximum kinetic energy. Now, the notion is, why is this called Ke max? By the way, what is maximum kinetic energy? What is Kmax? It is simply energy left with the electron after being set free from the orbit in the metal. Let's simplify it. After being set free from the metal when it has escaped. So it is the excess energy with the electron. Where did this excess energy come from? It came from the light wave itself. So the light waves had more frequency than the threshold frequency. So there was excess energy transferred to the electrons. Hence, they have a certain kinetic energy. And we this kinetic energy we call Ke max. Why is this called Ke max? The reason is all electrons that escape don't have the same kinetic energy. Each escape with different velocities. Why is that? Even if the thing is, sure, technically everyone should be, if all of the photons coming in are at, let's say, 6 into 10 to the power minus, sorry, 6 into 10 to the power 40 hertz, then all of the electrons should be transferred the same 33 joules of energy, let's say. Okay, but it doesn't happen. Why? So different electrons escape with different velocity because all electrons come from, for one thing, it, electrons that you hit may be from a lower orbit. So usually what happens, the majority of the cases what happens, or what we would like to happen is I just want the outer orbit electron to escape because that is easier to um, shoot out. But you also sometimes want lower orbit electrons to escape. And the energy required for this to escape will be, let's say, less than as compared to this one, the one closer to the nucleus. So different amounts of energy are required to emit the electrons in different orbits. So the reason I say K max, why do I say K max? The reason I say K max is because the electrons leave with a distribution of energy and a distribution of velocity. Reason is it is not always the outer orbit leaving, or not always the second last orbit leaving, or it is never certain that all of it will come from any one orbit. That is one point. Second point is um, the way the collisions are happening, number of collisions that are happening, that can vary as well. Things can come in its path, multiple collisions can take place, which is why the energy gets a bit distributed. So there's a peak, but for one thing, there will be multiple peaks often. And the second thing is the peaks are a bit sharp, but they have a range. The peaks have a range. That is the peaks of frequency at which you see, not the frequency, the peak of the kinetic energy. So if I'm plotting um, the kinetic energy of the electrons, what I will see is the kinetic energy of the electrons are actually very varied. Okay, they're not exactly one kinetic energy. It is pretty much a range of kinetic energy. The reason we take the K max is theoretically that is the maximum kinetic energy the electron should have when hit by this amount of, let's say, frequency. And that maximum kinetic energy in this case would be 3 joules. Theoretically, the particle, the electron itself, should have 3 joule of Ke, and we call this Ke max. However, however, it just happens to be that in real life it's less than that. Because for one thing, there can be multiple collisions, energy may be lost. Energy may be lost for a lot of reasons, by the way. And the second thing is it may be multiple orbits leaving the atom. Okay, electrons from multiple orbits may be leaving the atom, which is why it is a distribution of energy that is kinetic energy that we see of the particles. Okay, good. Give me a moment, please. Okay, so as I was saying, that the kinetic energy can vary. That is the sole point I want to put across. And that is why we take the theoretical maximum value. That is, we subtract the energy provided that is through the EM wave, minus we take away the threshold energy. Okay. And whatever is left over, it's the leftover energy for the electron, which is Kmax. Okay. And you will see this formula very soon. Now, the third thing that I want to talk about over here, next thing I want to talk about is if you increase the frequency of the light waves, that is, you increase from red light to, let's say, violet, this wouldn't increase the number of electron emitted. This would not increase the number of electrons emitted. Why is that? Because one photon only hits one electron. That is a fundamental rule. So when this photon is hitting this electron, the photon transfers all of its energy to this electron. So there is a one on one collision. Okay. Which is why increasing the frequency of the light itself or the photon itself doesn't increase the number of electrons, because one photon will only transfer energy to the one electron. It won't transfer energy to multiple electrons. So the number of electrons that emit are the same. It is just that those electrons will be having a higher kinetic energy, Kmax. Okay, very important statement. So if you do want more electrons, that is photoelectrons, to escape, what do you do really? What you do is you increase the intensity of light, in the sense that you increase the number of photons shown on the metal surface. Got it? So if you do that, then yes, more electrons emitted. Okay, good. Okay, so we increase the number of photons. Okay. So yes, again, in return, if you have higher number of photons, more electrons released, so rate of emission increases of the photoelectrons. Now, a couple of definition. What are the definitions? I'll explain. For one thing, there's something called the threshold frequency, minimum frequency of incident electromagnetic radiation required to remove a photoelectron from the surface of the metal. So we tend to say surface of the metal, and in essence, that what it means is electrons from the outermost shell of it. Okay, so yeah, minimum threshold frequency in essence means the minimum frequency required of an incident electromagnetic wave. Okay, um, to remove a photon, sorry, to remove an electron from the outermost shell. Okay, usually. So it can be that lower orbits are released, but in those cases, you need to provide more energy. Okay. So yeah, if you're providing multiple wavelengths of light, then yeah, you will see multiple peaks. That is to say, if you have so you're providing multiple frequency. Okay. So if you have a plot of frequency over here, and number of photoelectrons, then you will see multiple peaks. One peak here, one peak here. I don't think the peaks should be sharp, is what I believe. Okay. And all of these peaks, it will look different in your, whatever the real experiment is. But all of these peaks inherently says these are transfers of electrons, either from outermost to completely out of the atom, or innermost, let's say innermost here to the second orbit, or innermost to third orbit, or innermost to exiting the atom. All of these transfers of electrons show up as, let's say, the peak. Okay, fair, good. So essentially, there's a certain frequency required for the electrons to escape, and that is called the threshold frequency. And usually, we're talking about the outermost orbit of the metal, and we provide that much energy. So that is the threshold frequency to constitute to the threshold energy. And what is the threshold wavelength? If you have a threshold frequency, obviously you have a threshold wavelength. You need to understand this very well. Why do you need to understand this very well? The reason you need to understand this very well is they will ask questions where they will ask you, if I do X, what happens to the threshold wavelength? So they can ask you questions with respect to threshold wavelength and not threshold frequency. So you have to understand the concept of threshold frequency. Sorry, threshold wavelength. So let's say your energy is HF, right? Very good. So F I can express as V is equals to F lambda, right? So if your frequency increases, your wavelength decreases, right? So if you have a high frequency, that is high energy. Okay, I can substitute F with C by lambda. Can I do that? Because velocity is F by lambda. Can I do this, guys? Yeah. So frequency is velocity by lambda. I'll substitute this and I get to 8c by lambda. Good. So my point is, if I increase the wavelength, what happens? Your energy decreases. It is very simple why this happens, because if you increase the wavelength, your frequency decreases. So ultimately, it is an inverse proportion between what happens uh, to energy when wavelength is increased, as opposed to what happens to energy when frequency is increased. If frequency is increased, energy increases. If wavelength is increased, energy decreases. Good, good. I hopefully you understand. So there is a maximum wavelength. Okay, so the threshold wavelength, in essence, is the longest wavelength of the incident EM radiation that would remove a photoelectron uh, from the surface of the metal. So the longest wavelength basically means the smallest amount of energy. Okay, think about this. Do think about this. It may be a bit counterintuitive, but try to think about this. It should make sense. And what is work function? Work function is the minimum energy. I kept saying minimum energy, but the proper word is work function. So the minimum energy required to release photon from the surface of a material. There is the formula of work function. Work function is defined as Planck's constant times threshold frequency. Okay. Work function is expressed as Planck's constant times threshold frequency, hc by lambda naught. You can also express it as this. So I basically, F naught, I have expressed it as c by lambda naught. Okay. This is threshold wavelength. You can also express it as this, phi. Good. Yeah. So let's set up the experiment really. Okay. Let us set up the experiment. Okay. This is important. Important. If particle duality, loss of averages. Okay. Oh, there's quite a bit. Anyways, right. So let's set up the experiment where we get to understand what's happening. Fair. So what is happening in such a case? We have set up an experiment to understand the particle nature of light. Okay. So to establish the idea that light has something called photons, we carry this experiment out. Because what I established above is I told you guys that if XYZ happens, then it easily means that it is a photon. So I told you guys that When there is one-on-one emission, that obviously means that light is traveling as a photon. Because if there is a transfer of energy like that, for example, you have two balls, one ball comes in with velocity and then hits this ball, and both are with, let's say, some certain amount of mass, it will transfer its energy to this and it will start moving. Practically, that is what's going to happen, right? So essentially, my point is that if all of these are true, it is obvious that light has particle nature or they travel as photons. So you have to accept that when we prove all of this. I established that these are the observation, but how does it happen? Let's see. How it happens is, let's say I have basically I'm showing you the experimental setup. This is a cathode filled with negative charge. This is an anode, okay, and then it is connected by wire to this one loop. And in this one loop, I have millivoltmeter. So it is measuring the voltage in this entire circuit. And then the second loop, what I have essentially, and this is the voltmeter simply, and this is essentially the circuit itself, the outer box. So I have a cell, which is a variable cell. I can increase or decrease the power supply nonetheless. And this is a milliamp meter. So we can measure the current in the circuit. Very good. So what is happening? Oh, by the way, there is also a transparent vacuum chamber. Okay. So it essentially controls the permittivity in space. Okay. So that there is no air. I taught you guys about permittivity or how it affects transfer of electrons or electric fields in general. So yeah, there's a vacuum chamber over here. Good. So number one, the light is shown on the zinc plate. There's EM wave coming in on the zinc plate, right? Good, because they have the electrons, they have the supply of electrons, and the photoelectric emission takes place and electrons leave the plate. So from this plate, electrons are leaving to where? There's electric fields. So electric fields will be in this direction, but we're talking about the movement of electrons. So electrons are moving towards the positive plate, of course. Okay, so now the electrons could go to the receiver or in any other direction. Since we have a battery, it sets up a positive terminal on the receiver, and all the electrons will, obviously, irrespective of the direction, it will get attracted towards the receiver ultimately. So notice positive terminal establishes a positive terminal, negative terminal establishes a negative terminal on the zinc plate, which is the cathode. Very good. So this is how it works. This is how the all the electrons are being attracted to the positive plate. Makes sense to you all? Hopefully. Good, good. So since the receiver attracts electrons, it acts as the anode because it is gaining the electrons. And since zinc plates emits the electron, it acts as the cathode. Makes sense. And you have the microvoltmeter, which is measuring the voltage or the potential difference set by the battery, and you have the ammeter, which is measuring the current in the circuit. Okay, and this can be used to find the number of electrons flowing. That is to say, I is essentially rate of flow of electrons. Can I not see this? Yes, I can see this. Okay, so it is the rate of flow of electrons essentially in some sense. Now, when this entire thing is done in a vacuum chamber, there is no air molecule, and essentially this helps our electrons being attracted to the receiving side, that is the anode. Okay, and it is also true that we want it to be transparent, and for obvious reason, because we want light to pass through it, right? So if it was opaque, then obviously light wouldn't be able to pass through the vacuum chamber. Now, why is there a variable power supply? Let's explain that as well. Um, let's say I have an anode where I am not being able to control the charge, and let's say the charge is pretty low. And what would happen is some of the electrons will escape out, and there won't be attracted by the receiver, and we would have a false information about how many photoelectrons are being emitted. So we want to make sure any amount of electrons that is emitted, I have it on the receiver. Make sense? So I want to be able to vary the potential on the receiver, the amount of charge on the receiver, positive charge. Fair. So we need to increase the voltage of the cell to make the receiver more positive until the current stops increasing. What does this mean? Try to make sense of this. Right? So basically, as I mentioned, I want all of the electrons to be attracted to the receiver. So I keep increasing the charge on the positive plate by increasing the potential difference across these 2 points. That is, by increasing the potential difference supply. And what am I doing essentially? I'm increasing the potential difference, I'm increasing the positive charge over here until I see that in this entire process of constant supply of EM radiation, in this entire process of constant supply of EM radiation, I will keep increasing the variable potential difference supply until I see a plateau over here. That is, I have on the y-axis the current in the wire, and on the x-axis I have the voltage. So I keep increasing the voltage until I see the current plateauing or becoming a flat line. So initially over here, the receiver is not receiving all the electrons. Some electrons are going to the receiver and some are just escaping. Like keep increasing the voltage until until the receiver is positive enough such that it attracts all the electrons. Okay. So the max current tells us the rate of emission, the total amount of electrons being emitted per unit time. Okay. So now this is the right value of number of photo electrons emitted. Right? So over here, if you change frequency now, at this point, when you have established a flat line, there's a constant current. What do? We will try increasing frequency of the light. That is, I change from red to, let's say, violet. You know what we will see? We will see no change in current. Do you think we will see any change in current? No, because number of electrons traveling don't change. If you increase the frequency, number of electrons will not change, will not increase. It will be constant. It will be same. Okay. Only the Ke will increase. Fair. So if we have to plot a bunch of graphs, I'll show it to you. It wouldn't vary the amount of current. So where is that graph? Okay. Yeah. So if I increase the frequency, the current same as before. So if this is threshold frequency, by the way, notice before the threshold frequency, do you see any current? No, because electrons are not being emitted. Make sense? So the moment I have threshold frequency coming in from the light source, I see a current, and that current stays constant no matter how much I increase the frequency of the light. As I go from red to, let's say, violet. Current in the wire doesn't change. Why? Because number of electron does not change. And this is a very interesting experiment, a very clever setup. But yeah, before I show you more graphs, I will cover a bit more. What do I want to cover? I want to cover this. What is the notion of intensity in the photoelectric experiment? One photon, one P will hit one electron only. Okay, so one transfer. Number of photon intensity can only increase the number of electrons emitted. If the frequency is increased above threshold frequency, that is, it is transferring a greater maximum kinetic energy, more electrons will not be emitted just because of a greater frequency. And this is something we have established. Now, intensity is essentially what? Yeah, it is watt. It is power per unit area. Okay. What is intensity? It is simply power over area. How concentrated the power is. How what? How concentrated the power is. That's what intensity is essentially. So power I can explain as what? What is it? What is this analogous to? Power is work done per unit time, right? And area is area. And basically, what is work done? The total energy of all photons. Okay, per unit time. So when I have metal plate and light is coming in. How intense is this light? How intense is this light? Power per unit area. So if this is occupying this area, power per unit area. What is power? The number of photons hitting times the energy of all of those photons. That is the total energy. So number of photons coming in and hitting and the energy of each photon. Both of them multiplied will give me total work done, right? And by the way, T came to the denominator because, well, we have work done by time and then area. Obviously, it's work done by time times or divided by area, hence multiplied by 1 by A, hence work done by T times A. Make sense to you? Perfect. So that is why T and A is in the denominator. Perfect. Now, why is it NHF, number of photons, time total energy of each photon? That is the total work done, total energy. So intensity is proportional to number of the photons. Now, over here, you can also say the intensity of the amount of energy, right, of the intensity of light being shown on the plate can be varied by increasing the energy. Yes, the power per unit to area can be increased 100%. This is a question that will come your way. I've seen this question and it confuses a lot of people. You can increase the kinetic, sorry, you can increase the frequency, as you can see over here, increase the frequency, increase the intensity. But when you're not changing the number of photons, only changing frequency and increasing intensity by just changing the frequency, number of electrons emitted will not vary. Please understand that. This gets confusing for a lot of people. They hear intensity and what they understand is intensity is the number of photons hitting only. No, intensity comprises of power per unit area. Power can be explained as the total work done per unit time per unit area. And essentially the total work done can be expressed as number of particles times each particle's energy. You have to understand that. Okay, so if you just increase the frequency of the particles, intensity increases, power per unit area increases, but that does not mean more electrons will emit. You have to make sure number of photons has to increase. The frequency changes or not is a different conversation, but if the number of photon increases, inherently number of electrons emitted will also increase. So number of photons you have to increase for more electrons being emptied. This is something you need to clarify, understand, and just memorize in a way. You have to understand it first, and automatically you'll remember. Nonetheless, if in that entire setup, same setup, I have plotted the maximum kinetic energy. Uh, yeah, if I plot the maximum kinetic energy versus frequency, there's frequency of the particle of the photon. What does it look like? This is Kmax of emitted photoelectrons. And this axis, I have frequency. I have what? I have frequency. Good? Makes sense to you? Okay. Give me a minute, please. Right. So as I was saying, what? Oh, okay. Give me 1 second. So yes, as I was saying, where is this? Yeah. So as I was saying, if you increase the individual frequency, that is of the incoming light waves, if you increase the frequency, then the energy with which the electrons will emit from the, well, metal itself will increase. So Kmax increases as you increase the frequency of photons coming in. Now, what happens if, well, intensity is increased? Okay, if just the intensity is increased. Granted, my frequency is a constant. Okay, frequency is greater than the threshold frequency and a constant. What does this look like in terms of formula? Intensity I is expressed as n number of um, photons times hf divided by ta, and it is a given to you that frequency is constant. Okay, I'm establishing that frequency is a constant, let's say. Okay, and all I'm changing is number of photon. And then does this change the Kmax? No. There is a certain Kmax because the frequency, granted, the frequency is greater than the threshold frequency. There is a certain Kmax, this much, and it stays constant no matter how high the intensity increases. That is, number of photons increases. Because I've given you that the frequency is a constant. Frequency I'm not changing, it is a constant. All I'm changing is the number of photons. In that case, as we increase intensity, Kmax doesn't change. Next, current versus frequency. I just told you guys, if you increase the frequency, right? Frequency of the photon, it is simply that the electrons release with more kinetic energy, but the number of electrons emitted doesn't change. Valid? It does not change. So the current stays constant. Initially, before the threshold frequency, obviously zero, but after the threshold frequency, some current and it stays constant. And what happens to the current when I am increasing intensity? That is keeping the frequency constant. So let's say I is again NHF divided by TA. If I'm increasing the um, number of, this is a constant, frequency is a constant, I'm increasing the number of photons, the current will also increase because ultimately, if more photons mean more electrons, hence more current. Make sense? So these are, in summary, all the things you need to understand, especially with the photoelectric effect. A lot of content covered, very dense. Hopefully, makes sense. Now comes the photoelectric equation. Okay, a bit complicated, not complicated. It is basically putting all of the things into an equation that we know of. Right. So we'll be using the same formulas to combine into a standard formula by definition. Energy of a photon is h times f. This energy is transferred to the electron by the photon. Comes the photon, there's a metal, electron receives the energy and is emitted, photoelectron. So if the energy is greater than the work function energy, that is the minimum energy required for the electron to escape, then that excess energy becomes the kinetic energy. We have established multiple times in multiple scenarios. The total energy provided will be the HF, that is the frequency of the photon times the Planck's constant is the energy of the photon coming in, the waves coming in. Fair. So the total energy provided is equals to the threshold energy of the electron. So electron's threshold energy, that is work function, plus the Ke max. Ke max. So the total energy provided by the photon is distributed between the work function, that is the energy for the electron to escape, plus the kinetic energy of the electron after escaping. The sum of both of these gives me the total energy provided by the photon. Okay, total energy provided by the photon, energy to escape for the electron, and the energy the electron escapes with. Okay, so this is the standard equation. This is the energy supplied by the photon, energy to release, that is work function, and this is the excess energy. Okay, Kmax. So from this we can plot a graph. E is equals to h f naught plus k max. So if I make k max the subject, I have hf naught minus hf. So this hf is basically the energy supplied. Good. So I'm basically now going to consider Ke max is basically going to be. Oh, by the way, this is a minus sign, so I can multiply a minus sign on either side. So K max will essentially be HF minus HF naught. This is a work function, HF naught. This is the energy supplied, and this is the K max, which you have realized. So now I can consider this entire part as a constant C, H as the gradient M, F as the X variable, and K max as a Y dependent variable. Make sense to you? So now if I plot this, that is the y dependent variable, the x the independent variable. So as I change the frequency, the energy K max of the photoelectrons increase. So initially at the threshold frequency, it is emitted, that is the electrons are emitted, and as I increase the frequency, essentially, the amount of K max, the energy with which the photoelectrons emit, are increasing gradually. The gradient of this gives me the Planck's constant. And this is what I was talking to you guys about, that if you do these experiments and you find the gradient, that is essentially the Planck's constant. Okay, so the gradient is Planck's constant. This is a very common experiment. Okay, by the way, what is this? Minus HF. So this is negative work function. This is a question I've seen somewhere. What is this? This is the negative work function. Okay. So this is work function, but negative. That's it. Because over here, due to the sign change, this is a minus sign in front. Okay. Makes sense. Does all of it make sense? Are you clear? All good? Any confusion till this point? Okay. Okay. So we have completed most of the technical parts or math parts of the quantum physics chapter. There is a bit more in the line spectra part where we have to consider energy transfers. Other than that, there's not much. Okay. And now let's talk more about theory. Wave particle duality. So this is where we stop just looking at light and we start looking at other particles as well. So light, we have established, acts both like a classical wave and also like a um, particle itself. So it has both nature, wave-like and particle-like nature. Particle-like nature we have expressed with photoelectric effect. We can also talk about diffraction and or interference to talk about it as classical waves. Fair. Okay. So now what we're going to discuss is the difference or the sort of points that we have of the particle properties of light waves, that is the photons, and also the wave properties of light in general. So let's just allocate the points as to what we understand of light, why it is particle, why it is wave-like. So why is it wave-like? Because in general, particles tend to have a mass, hence a momentum. So why is it that we don't feel that there's a mass hitting us when there is sun shining its light on us? We don't feel any sort of mass hitting us. We don't. We feel it's warm. We feel our skin is burning, but it's not like I feel any amount of heaviness on me when the sun is shining on me. But why is that? We're saying that well, light has particle properties. Okay, photons are particles, but we also say it's massless. So how is it possible if it's a particle we don't feel heavy when being on the sun? So it is simply the fact that photons are massless. Photons don't have a mass, but it apparently has a momentum. And this is very, 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 very crucial. Very crucial. That it turns out it is a particle. Apparently, it is a particle, no mass, but there is momentum. And this is a very important discovery and understanding. And Einstein worked on this. So you guys must have heard of the general relativity, relativistic view, uh, and we consider these things over there. I'll give you a glimpse of it right now, very soon. But it's very interesting over there that things are actually comprised of, yeah, you can consider their mass, but you can purely consider its energy as a mass equivalence. And the formula for different scenarios sort of changes. When we're talking about light, we consider some aspects of the equation, and we're considering particles itself, other particles. We consider some other aspects of the equation or the entire equation. So I'll explain what I really mean. I'll show it. So yeah, essentially the particle is supposed to have a mass and a momentum, but in our case for light, it doesn't have a mass, but it indeed has a momentum, and we'll show this to you. So, the other feature of having particle-like feature is it has a position. So, in general, when we think of classical waves, as I was saying, we think of it as a continuous stream of energy, constant energy stream. It is continuously providing some amount of energy. So we see it as a constant stream of energy. But in in case of light, it is a discrete or quantized source of energy. One particle, one photon is transferring a certain quantized amount of energy. So yeah, quantized was the right word. Anyways, so quantized basically means that there has to be a specific number of photons and uh, they're individual. So electrons, the number of electrons, it is a quantized thing. So there has to be specific integer value of when we're talking about how many electrons. Okay. So yeah. Now, if there is a certain number of particles when we're talking about light, then all of these particles, all of these photons have a certain position. That's the interesting part. So if it's a particle, then it has to have a mass or a momentum, and it has to have a position. Great. And in case of a wave, it's simple. It comprises of oscillation, that it has to have a frequency and it has to have a wavelength. And if it has a wavelength, it will simply diffract. That is one of the very basic ways to look at it. Now, light apparently turns out to exhibit both properties. So, in case of photoelectric effect, what do we see? We see the particle properties. So when we talk about diffraction, we see wave properties. And now we can also talk about individual particles other than, let's say, photons. Let's talk about electrons. Now, do electrons as an individual particle, we know electrons are particles. Do electrons also exhibit wave-like properties? So is it that all particles in the universe have some amount of a wavelength? That's what we are going to figure out right now. So towards the beginning of the class, I said that it is, anything out there, it has a wave-like feature and a particle feature, in essence. So let's go through this entire thing. What do we have? What kind of a setup do we have? The setup we have is it is an electron gun. It shoots out electrons, and there's a negative charge over here, positive charge over here. That basically creates a potential difference. And what is the benefit of creating this potential difference? When the electrons are shot out, it basically gets attracted to the other side. Hence, it is accelerated through this entire area. It is what accelerated through that area. So it accelerates the electrons and it shoots out electrons. As it shoots out the electrons, what happens is when it goes through this graphite target, there are small slits in the graphite target. That is, we didn't make the slits. It is essentially that, if we take a microscopic view of, let's say, graphite, so there are, well, nucleus, 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 and then there's an atom. Okay, electrons, atom, electrons, atom, electrons, atom, electrons. So each orbit has electrons. Now, what happens is when electrons are shot in, it bends in multiple directions. So the slit essentially is the space between the atom. That is the slit for the electron when it is being shot through graphite. Is that clear? Okay, so it diffracts as it proceeds through the space between the atoms of the graphite. Good. So what is this entire process? And before the process, let me show you the result. So as electrons pass through the slits, compared to the typical example, when you have water wave fronts going in, multiple water wave fronts going in, so it's a wave. These are the crests, and the space in between are the troughs. So as it goes through this entire space, it bends. It bends, and this is a diffraction. Obviously, diffraction. So good. So this is the example we're comparing to. So electrons are coming in as particles, and it is going through the spaces, right? And as it goes through that space, it diffracts at multiple angles. So this diffraction is essentially happening even with electrons, and it diffracts literally in 360 degrees. That is to say, it creates multiple circles, or you can say concentric circles. That is, the center is shared, a single center is shared between all the circles. Um, so this is the thing that we see. So, what I'll show as well, in essence, electron diffraction. So, for example, look at this. For example, this. So there will be multiple concentric circles denoting the diffraction of the electrons. So you see, so these bright spots essentially are the places where the electrons hit. So it's very fascinating and interesting how the electrons got diffracted into creating this um, shape. These are concentric circles, and it's very similar to how, in general, diffraction takes place, right? So yeah, I do find it very interesting, and what other ways? So look at this, a very great example. Electrons are pushed in. These are slits. It is going in, and it creates this pulse. Uh, yeah, again, another example. These are the concentric circles. Very interesting. So these are essentially, it actually glows in green. For example, this is great. So there's some fluorescent material in the, did I write it? Yeah, there's a fluorescent screen that when electrons hit, it glows in bright green. So the bright green that you see, this is the area where the electrons hit. Center is the highest concentration, and then there are other circles beyond. So you know how interference takes place. there is the center and center. And then beyond this, oops, there are other maximas. Beyond the central maximas, there are other local maximas. Okay, now what is happening over here? There's a high voltage between the electron gun and the target, usually in kilovolts, and this accelerates the electrons. Perfect. As the electron gun shoots, the electrons uh, get scattered around. Okay, and diffracted. Both happens, by the way. Scattering happens and also diffraction happens. Scattering in the sense that electrons are just moving in multiple directions due to the collision with the basically atoms in the graphite. Some pass through the slit space between the atoms and diffract, and some will collide with the atoms and will scatter. So how they scatter? The electrons basically pass through the gaps between the atoms of the graphite. Those act as 3D slit. Now, as electrons pass, they are mostly attracted by the nucleus of the graphite around the electron. So this is why we see a bunch of electron at the middle. Here, the intensity of electron is the highest due to scattering, that is electrostatic attraction. Okay, so it is also possible that electrons are scattered in other direction. However, as you increase away from the center point, the amount of scattering in all of those other spaces will decrease. And that is due to the lack of attraction. So in general, scattering, what we think of is spread of the particles due to some amount of a collision. Now, when I say it is colliding with the atom, how is it colliding? It is basically an interaction of the electric field, or it is the attraction and repulsion of the charges. That is how it essentially is hitting the atom, right? So an atom is essentially a bunch of space, right? So when you are hitting the atom, essentially it is some sort of a attraction or repulsion with the atom. So this force that is applied on the electron coming in, electron comes in, right? And it goes through the graphite slit. It hits the atom. Let's not say hits the atom, or it gets some sort of repulsion attraction with the atom, and some sort of an electrostatic force is applied on it, and it gets scattered around the center point and other points as well. It's a bit random, but as you increase the theta away from the center point, that is, as you increase the theta from the central maxima, the amount of scattering is less. So scattering does take place. Scattering takes place, but less beyond the central point. Now, scattering, I understand. So essentially, by scattering, don't look at these rings. Don't think of these rings. So these three rings, don't think. But the background green, do you see? Background green, do you see this light green? So towards the middle, it is very bright, and the background green, as you move away from the center, gets darker. That is due to scattering. That is due to scattering. And these concentric bright circles are due to diffraction. That is the difference between having the scattering and having diffraction. That's a very good picture. Okay, so how is diffraction taking place, by the way? So let's say in a situation that diffraction doesn't take place, what would you expect to see? Just this green background, none of these rings, none of these rings. Clear? Because I just explained that the background is due to the scattering, and these rings are due to diffraction. So if diffraction doesn't take place, I only get the scattering bit. Right? So basically, electrons are getting diffracted. And why is that happening? Because of the wave-like feature that they carry. So electrons, it turns out to be that they also carry wave-like features. And in this experiment, due to having the diffraction, it is proving that electrons indeed do have wave-like features. So when they're passing through the slits or space between the atoms, they're diffracting. Okay? And this is essentially, this was experimented or thought of hypothesis. Yeah, sorry. So yeah, this was hypothesized by D. Broglie. I don't know how it's D. Broglie, D. Broglie, whatever you want to call it. But yeah, this was thought of, experimented, and we also call it D. Broglie's wavelength, which you see over here. So the main breakthrough over here is sure, light acts as a particle and as a wave as well. But the interesting thing is other particles like electrons and also literally any other thing apparently has a wavelength. This is the interesting bit. So, how are they diffracted? The answer is they have a wavelength. Electrons have a wavelength. That is why they're diffracted. As they move through a space, they have a wavelength. That's why they're diffracted. So, essentially, now, point is if electrons can have a wavelength, so can other particles. That is the point. So de Broglie expresses this wavelength using the following formula, which is lambda is equals to, that is de Broglie's wavelength, that is wavelength of any particle is equal to Planck's constant divided by the momentum. Okay. Now you will argue that why is it that my water bottle, me, we don't, it doesn't, I can't see the wave at all. And the reason you can't see it is because either it's stationary or when it has a momentum, it's a high momentum. Okay, it has a high momentum. And that is why, in such a case, the de Broglie wavelength is extremely small. So you don't see it, essentially. That is the point. Okay, so de Broglie wavelength says whenever there's a momentum, any sort of momentum, there must be a wavelength attached to it. So when you see the fluorescent screen light up, it's basically electrons hitting it, right? So the more electrons hit, the brighter it gets. Now, when you have a low voltage, by the way, this is something you need to understand. By the way, what is this showing? So it's showing from the central maxima to here. So this is central maxima. Then there is n is equals to one. There is n is equals to one. Then so on and so forth. So something like that. So there are multiple peaks. Okay, that is what the wave is. Not too complicated. So now, what happens when you have a high voltage? How does it affect the diffraction? When you have a low voltage, um, the concentric circles are further apart. Why is that? Let's see. High voltage, okay. High, sorry, what are we talking about? Low voltage? Yeah, low voltage. Low voltage means less acceleration. Okay. And what do we see in low voltage? We have more farther apart. Okay. More farther apart in, if you have low voltage, you have the rings interference pattern more farther apart, and the voltage, that is the acceleration taking place, is low. Okay, the acceleration is low, which means easy to diffract. Okay, essentially this is the thing. You have low voltage. What we see is the interference patterns are more farther apart because the acceleration of the electrons are low, and due to the acceleration of the electrons being low, it is easy to diffract the electrons. Okay, we can also quantify in this entire expression, I mean, whatever we just talked about, that how is it that the voltage has this effect. And I guess this is going to be a more important way to look at it. But I will also give you, I'm trying to paint a intuitive picture. This is a pretty broad. I don't know if this entire thing, yeah, this is in your syllabus. Yeah. So I'll explain the voltage bit in terms of the equation as well, but I'm trying to give you an intuitive idea. So again, if you have high voltage, think of it this way: less farther apart. Okay. So acceleration is high, hence harder to diffract. Now, this is the qualitative way of looking at things. This is one way you could sort of think of it. Now, the other thing is, let's look at it with the lens of equations and numbers. And I believe this is the better way to go about it because it makes sense. Now, how to prove that high voltage means that the circles will be closer together. So we know that the voltage applied accelerates electrons and provides it with energy, and more specifically kinetic energy. So as it accelerates, it has more kinetic energy. And we know that the voltage is work done per unit charge. So here the work done is basically transferring whatever the voltage is into kinetic energy. So whatever the Ke that the electron has, if it's going from rest, that is at this end of the electron gun, to being accelerated in this entire space. So at this end point, the electron will have a certain speed and will have a certain kinetic energy if it's going from rest to a certain amount. Anyways, so the kinetic energy supplied will simply be the amount of charge passing through it uh, and the voltage it is going through. So we're going to think of it as one electron passing through. How much energy is being provided to that? So the kinetic energy of this electron will essentially be the electron times the voltage it is going through it. So I can say half mv square is equals to EV. This is energy supplied to one electron. And we know that lambda can be expressed as, or that is the wavelength of a electron, I mean any particle can be expressed as the Planck's constant divided by the momentum. And I'm going to be plugging in momentum is equals to mv into the same equation. And if I do that, I have lambda is equals to h by mv because I plugged in p as mv. So this is one equation that you need to be aware of. This is the second one. One we have equated Ke to the voltage that an electron goes through, which is the energy supply, and it turns into kinetic energy of the particle. And over here, I'm basically expressing the wavelength of the electron as in terms of h, m, and v. So from the relation 1, we can say that as the voltage is increased, the kinetic energy increases, so the velocity increases. So applying that logic to 2, if the velocity is increasing, there's a decrease in wavelength. If I increase the velocity, there's a decreasing wavelength of the electron. From this, we can include, in essence, that if I have a smaller wavelength, that simply means the spreading will be smaller. Have you guys heard of this? High wavelength means more diffraction. Okay? So when you have a higher wavelength, you have a higher diffraction, more diffraction. You guys must have heard of red being more easily diffracted than violet because it has a higher wavelength. Clear? Good. So if I further want to prove this, let's say this is the slit equation, that is a diffraction equation. D is basically the space between the atoms, that is a slit. This is D, slit between the atoms. D sine theta is equals to n lambda. As I decrease the lambda, that is wavelength coming through the slit, the theta at which it is diffracted is less. Okay, so if I combine all of these together, I know energy is equals to half mv squared. That is, I am expressing energy in terms of 2e as mv squared. I'm taking 2 to the other side, and velocity I can express as essentially 2e by m root over. Okay, and lambda is equals to h by mv, which we established over here. And I'm going to plug that in. Okay, so I'm going to be putting in velocity into here. So lambda is going to be h by, oh well, m 2e by m. Okay, okay. Lambda is essentially then going to be h by root over 2me. How did I do that? How did this step happen from 1 to 3? Sorry, 1 to 2. How did this step happen? If you're confused, I will clear your confusion. So m times root over 2 times root over e divided by root over m. I basically put the root over all of these variables. Can I do that? 100% I can do that. This root over is on all of these variables. So I put the root over individually on 2, e, and m. Clear? That is what I did, 2, e, and m. So basically, m has a power of 1. Here, m has a power of half. So use indices law. M1 minus half essentially is going to be m to the power half in the numerator here. So lambda is going to be h by m root times 2 root times root e. So essentially, ultimately, lambda becomes h by root over m2e. Is this okay? I can also write as number and alphabets. Okay, is this clear? This entire process is clear? Hopefully it is. So, what did I express now? An equation of lambda, that is of the electron. If I know the mass of the electron and the energy it is carrying, I know the lambda of the electron. This is quite fascinating, I would say. Okay. So how did we express that voltage changes the diffraction pattern? With this relationship. Lambda coming in small, the separation will be small. When is lambda coming in small? When the velocity is high. When is the velocity high? When the acceleration is high. When is the acceleration high? When the voltage applied is high. So again, what I said stands true. If you have a high voltage, yeah, when you have a high voltage, less further apart, acceleration is high, hence your concentric circles are closer together. Right? High acceleration, as in high voltage, means less separation between the circles. That is less diffracted. And I just proved it to you using multiple steps. And this last bit that you have is expressing the wavelength in terms of Planck's constant, mass, and energy that the particle has. So if you know E, E is basically the energy supplied between the accelerator. Not, yeah, you could say accelerator. So the energy supplied over here, that is between the plates, right? So when you are accelerating the electron, you're providing it with the energy. You're doing what? You're providing the energy. So whatever energy you're providing, whatever electron volt value you're providing, times the mass of electron, and that is all you need to understand what is the wavelength of electron. That is literally it. Done. Nothing else. Okay, perfect. Now your question may be, how can photons have uh, any sort of a momentum, right? It doesn't have a mass. There is another question to answer. Well, if momentum is expressed as m times v, and if m is zero, momentum should be zero, no? Makes perfect sense. However, this is not the entire truth, okay? And the reason I say this is, remember a few minutes before I was saying that things traveling like a light and things which are static, like your water bottle in front of your pen, these are different situations, and you can't have the same um, equation express the state of both of these particles, one traveling at the speed of light, one stationary in front of you. So essentially, there's a relativistic view and there's a non-relativistic view of things. You don't need to get, even I haven't studied it as much. So you don't even need to fully comprehend it. Okay. What you need to understand is this equation is not necessarily true when we're having a conversation about light. Okay, so what our ancestors, specifically talking about Einstein, has figured out is there's a very interesting relationship between energy of any sort of particle that can travel at speed of light or speed of light, and he has summed it up into one universal equation. So it is the relationship of essentially the momentum. And you can see the video over here deriving Einstein's E equals to mc square formula. But I've expressed it over here as well. So energy of a particle apparently is equal to the rest mass of the particle squared times speed of light to the fourth power plus momentum of the particle squared times speed of light squared. Make sense? It shouldn't make sense to you, but this is what I'm giving to you. Okay, so now according to this equation, if mass is zero, this gets cancelled. There is still a momentum, and that momentum is going to be root of e square is equals to p square c square. And if you take a root on either side, e is equals to pc. So essentially, the momentum is energy of the light particle divided by speed of light, and that is the momentum of the light particles. That is the momentum of the light particles. So it came from this equation itself that we got to the equation of momentum of light. Now, we can also use the same equation to derive de Broglie's wavelength for light. Let's do that. Let's try. And may be important. I may have seen question related to this. Okay. So E square, again, same equation. And what do? Light has no rest mass. That is, this part is zero. So P square, C square. And E, I can this part you're clear, this entire part you're clear, and I'm going to sub in E is equals to HF. Okay, this equation you know, as frequency increases, energy of the particle increases. So I plug this in over here, and I have H square, F square is equals to P square, C square. I take a root over on either side. I have HF is equals to PC. So I took a root over, root over. Perfect. Now, what do? I want to basically change a bunch of sides. So what I will be doing is I'll be subbing in. Before subbing in, I'll basically change the side to make my life a bit simpler. So all I'm doing is I'm bringing momentum to the left hand side, so h by p, and I'm taking this over here and this over here. That is essentially what I'm doing. So h by p and c by f. Wait a minute. So h by p and p by c. C by f. There's something wrong over here, most likely. Wait, let me continue. Let's see. So if that is the equation, h by b and c by f, essentially, what do I have next? I'm going to sub in lambda is equals to fc. So h by p is equals to inverse lambda. And then ultimately lambda is equals to be p by h. Have I done something wrong over here? Wait a minute. Okay. Yeah, I need to recheck something. It is indeed h by p, which is correct. Which is correct. HF, which is okay, and then p square, c square. Take a root. HF is equals to pc, and I divide by p, h by p. I divide by f, which is fine, and I should have c by p. I should have, sorry, c by f. Yes, lambda is equals to, okay, lambda. Oh, this is where it's wrong. Lambda is c by f, not f by c. C by f, lambda. Yeah, it's correct. My bad. Yeah, there was something wrong written over here. Oops. Lambda is c by f. C is equals to, let me recheck. Yeah, lambda is c by f indeed. Yeah, that's where it went wrong. Anyways, so yeah, this ultimate equation is correct. Something wrong happened over here in the substitution. So it is indeed going to be, so I divide by f, this is c by f. Okay, my bad, I have to correct this. C by f. Okay, Perfect. Now makes sense. Now I sub in lambda is equals to CF, and when I do that, lambda is equals to H by P. This is the correct equation. So from my point is, coming from this equation, this holistic equation, I get to my equation for the lambda or the wavelength for any particle, be it an electron, be it any random particle that you have on your um, table right now. Any particle has a certain wavelength and can be expressed as the Planck's constant divided by its momentum. Okay, so this expression we initially thought applies for waves as in light, but de Broglie basically came and said that, well, if electrons can also have this, then it can be that all other particles in the universe has some sort of a wavelength. Okay, so that's why it's called de Broglie's wavelength. Okay, so all particles, including electrons, tend to have a wavelength. Even you, even me, all of us. Okay, we're done with pretty much everything. We have very little left. We'll cover it tomorrow. Tomorrow is Sunday, and we'll be covering it tomorrow. Okay, all good. Any question till now?
No questions.
Perfect. Okay. See you next class tomorrow. Bye bye. Any question, feel free to post it in the classroom. Okay. Bye bye.
Bye.